learn calculus. I watched a few courses of professors and YouTubers explaining calculus, but I'm only going into 10th grade math, so why am I doing this? I'm actually submitting this video to 3 Blue 1 Brown and other YouTubers contest called Summer Expeditions of Math Explainers, or SOME Season 2, where the competition is for the best math explainer. That's the first reason why I decided to learn calculus. The other reason is just because I've always seen calculus in different math videos and always been like terrified because I didn't really know what the symbols meant. I didn't really understand it. So this summer I basically just put my foot down and said, hey, I just want to learn this. I don't want to be scared of it anymore. I don't want to not think about it because I don't understand it. I want to learn it, I want to understand it, and I want to appreciate this type of math. So this video is just my current understanding of what calculus is. And I am kind of cold, so let me just get a jacket on before I start. Okay. So let's start with the fundamentals. So position. What is position? Well, position is just where you are. For example, I'm right here talking to a camera, and you're sitting behind a computer screen watching me. That's your position, you're where. And maybe what we could do is talk about position, but over time. Like for example, I could start here, but then later, over time, I will go there. And we could plot that on a graph, like here, where as time moves by, the position goes up. Because like as time, you're getting more and more to the top. You start at the bottom, but over time, you go to the top. Okay, so now, what is velocity? Well, velocity is kind of like speed. It's like how quickly your position is changing. Like, for example, this graph, at the very start, as time is going along, the position isn't really changing that much. So that means the velocity is slow. But when you get to the middle, the position really starts to get higher and higher. So that means the velocity is up. But then at the end, as time goes by, it kind of plateaus. You start slowing down, so that means the velocity is low. Okay, so now, what is acceleration? Well, acceleration, just like velocity is to a position, acceleration is just how quickly velocity is changing. For example, here, at the first part of the graph, the object's velocity is going up, so that means it's accelerating, so it has positive acceleration, but the other half, the velocity is going down, so it's decelerating, it has negative acceleration. And in theory, we could just keep going up and up, adding new terms. I think the next one is jerk. Then I think the next ones up are like snap, crackle, pop or something like that. But anyway, you see we kind of have like this hierarchy of different like science terms, where one term explains how quickly the one lower down is moving. And what I want to really focus on in this video is this idea of rate of change. Because like, what is rate of change? And also we're going to be figuring out how to, if we have some graph, how we can get another graph out of it, how to find the rate of change of that graph, which that process is called differentiation, of taking one graph and finding its like velocity graph per se. Then what we're going to do is do the reverse of that. If we have like some velocity graph, we're going to try to find the position graph. Like do the reverse of differentiation, which we're going to call integration. And then where it starts to get really cool is instead of just having functions of like object's position over time, like have these functions, have these graphs be defined by formulas. Where if you have some input, the output is just defined by a formula with the input with given the input. So there's a lot of things in this video and I'm really excited to get started. Okay, so differentiation goes up and integration goes down. But the thing about integration though is that it's like broken. It's impossible. If you have a velocity graph, you cannot get one position graph out of a velocity graph. It's impossible. So let's just say you were given this velocity graph, which like it looks like it starts slow, then goes fast, then goes slow. That means that if I go slow, fast, slow, well I'd say that position graph matches up with this velocity graph. So like the velocity graph like kind of gives me the shape of the position graph, but who says it has to be in this room? In fact, who says it has to be in this state or country, or who says it has to be in this solar system. Like, there's nothing that tells you that. So yes, the velocity graph does give you the general shape of the position graph, but there's nothing in the velocity graph that gives you the general area of where the position graph is located. Because, like, technically, there are infinite position graphs that can come up with a velocity graph. But there's one velocity graph that can come up with infinite position graphs. So integration kind of has this property where if you have a velocity graph, it will give you infinite position graphs where all the position graphs have the same shape. So integration can only tell you stuff about shape, not where any one particular point is. What I mean by that is if I have a velocity graph and I want to find my position after 3 seconds, well, because that question asks about absolute location, I can't do that because we don't know anything about absolute location. But there is another question that I could ask where I give specific time inputs, where it asks about relative location, not absolute location, because we know what relative location is. We know what the shape is. That question being, what's the distance traveled between 2 points on the velocity graph? Because we know what the shape is. And we know what the distance traveled is, no matter where it is. Like right now, if I go slow, fast, slow, I know I traveled like about a meter. But if I go to like Tokyo on the other side of the world, then I go slow, fast, slow, I still travel a meter. Doesn't matter where my absolute location is. It only cares about what the general shape of the position graph is, which is all we could really know anyways. I think this question about the distance traveled between like some time interval will be like a really like useful question to ask, and maybe it might help us actually do integration. Okay, just to recap, so we have these two operations, differentiation and integration. And now I want to start to figure out how to compute these operations. So for example, how can we come up with a velocity graph with just looking at a position graph? And vice versa, how can we come up with a position graph with just looking at a velocity graph? Okay, so if we look at the position, and we look at the very beginning of the graph, we can see that the change in position isn't there. It's just pretty much the same up until like around here. So as time moves by, the position is pretty much the same. And we can see that right here because the line right here is just kind of shallow. It's not really moving. If we look in the middle, as time moves by, we can see that the position is really growing quickly. And we can see that by the line in the middle of the graph to be kind of steep. And at the end of the graph, we can see the line kind of plateaus, which means that the position kind of stays where it is. So it kind of looks like that if the position grows really quickly, if we were to graph that, then it would look like a really high slope. Because as time goes by, the position goes quickly. But if the position's growing really slowly, then it would look like more of a shallow graph. Because as time goes by, the position grows slowly. Then if you have an object that's going downwards, if it's like shrinking, if it's going in like the opposite direction, then you're going to have like a negative slope. Like as time goes by, the object's going to go down instead of up. And I know it's weird for like the talking about position growing and shrinking and stuff, but remember, position and velocity is just an example for like this rate of change idea. So it could just be like the stock market. If the price is going up, positive slope. If the price is going down, negative slope. Or anything really like that. Okay, so let's do it the other way around. If we have a velocity graph and we wanted to find a position graph, how might we compute it? So if we look at the beginning, we could see that the velocity is pretty low, which means that whatever object isn't really getting much position because the velocity is low. But if we look in the middle, we could see that the velocity is very high, which means that the object is gaining a lot of position all at once. But at the end, you could see that the velocity is really low, and the position is like trying to move, but it's a lot harder because like it's going really slow. The velocity is low. So you see that the object gets the majority of the position in the middle when the car's going really fast, but at the beginning, at the very end, it's not getting that much position. It's not getting that much position because the object is going really slow. But that's kind of really similar to like the area. Because right here, the majority of the area is in the middle, but there's a little area on the sides. So could the position be similar to the area. So the way I like to think about it is if you're trying to like squeegee the water off of your car after it just rained, and I actually got a squeegee to show you what I mean by that. And I know this is weird, but allow me to be able to change the width of the squeegee. So I make it like the width of the squeegee really small or really large. So if my squeegee was smaller, then I would only be able to cover a small amount of window every second. Then if my squeegee was larger, then I would be able to cover a lot more window every second, assuming that I'm squeegeeing at the same speed. Which means that I would be able to clean the window a lot faster with the bigger squeegee than I would have with the smaller squeegee, and assuming that I'm squeegeeing at the same speed. So it looks like that the rate at which I'm cleaning is relative to the size of the squeegee. So if we look at the velocity graph, we could, at the very beginning, we could see that the squeegee size is very small, which means that the rate at which we are building up area is slow. Like, we're building up area very slowly. Then if we look at the middle, we can see that the squeegee is very large, which means that we're able to build up area very quickly. And then finally, at the end, we can see that the squeegee is very small, which means that it's racketing up very little area. So it looks like that this graph represents the rate of change of the area under that graph. But this graph also represents the rate of change of this graph. So maybe if we have a velocity graph, but we want to come up with a position graph, it might be useful to look at the area under the graph, and that might help us find the position graph. Okay, so let's take a step back. So if we have a position graph, and we want to find a velocity graph, we could just look at the slope to figure out the velocity graph. And if we have a velocity graph and we want to figure out a position graph, we could just look at the area under the graph. But it's kind of weird that like slope of a graph and area under a graph are opposites. It's not really obvious when you first think about it. And actually, when I was learning calculus, when I was watching a lot of videos on it, there wasn't really a lot of information about why these facts were true. So it really took me a long time to actually think through it and really make sense of why these things are true, especially the area under curve correlating with integration. That, like, I knew it was true and I knew the math worked out if it was like that, but it just didn't feel 100% obvious to me. So now we know what geometric tools we can use to do the operations of differentiation and integration. Where differentiation goes from position to velocity, we're going to use slope in some way. And going from velocity to position, doing integration, we're going to use area in some way. But now what I want to figure out is how we're going to actually build out these graphs. Okay, so if you wanted to fill out some graph, let's just say that you have a position graph and you want to fill out a velocity graph. The way to fill out that velocity graph is to figure out the velocities for each point. And if you have a velocity graph and you want a position graph, you want to fill it out, instead of saying what's the entire graph, ask what's the position for any given value. Then if you're able to find the position for any given time, then you could just plug in all the different time, like all the different times in like your domain or like your input space, then you could fill out the graph. So how can we come up with a way where we can find the velocity or position at some time given? So let's start with differentiation first. So if we were given some time, then the way to figure out the velocity at that time is to figure out basically the slope at that point. Then if we go to velocity, the way we figure out the position at a given point, but remember when I said that you can't find a position at a given point on the velocity graph, right? And remember, instead of asking the question of finding the position at a given time, we asked the question of what was the distance traveled between two times, right? And if we go back to the squeegee example, it would be how much area was squeegeed from one time to another time. And if we go here, it's like how much area was gained from one time to another time. So if we want to find the distance traveled between one time and another time, so if this is time 1 and this is time 2, sorry, it's very sloppy. So the way to find the distance traveled between two time points, let's just say time 1 and time 2, what you do is find the area of the parts in the middle, or the area gained from one time to the next time. Now, while we're talking about the integration base operation, I just wanted to go over some housework about negatives and stuff. So what happens if, like, in somewhere in the graph, the velocity becomes negative, it dips below the time axis? Well, that means that the position is going in the opposite direction, it's going backwards. You are backtracking the progress that you have already made. Then if we think about the squeegee going from a positive velocity to a negative velocity, then it should make sense that the negative velocity is counterbalancing the positive velocity, or that when you have negative velocity, that the area should be counted as negative too. And in the same way, if the end point comes before the start point, then we should count that area as negative too. Alright, so now that we have our base operations, where if we are given some input, some time input, or two time inputs, then we could get the velocity at that time input, or the distance traveled between those two time inputs. Now that we have our base operations, what we can do is input all the different possible time inputs, then graph those to get our desired graph. So let's start with differentiation first. So what we could do is, if we have some time input, if we could find the velocity there and then graph it at that point where on the velocity curve. And because we could do this at any time, what we're going to do is do it at all times and find the velocities at all the different times, and then graph the velocities at all the different times. Then let's go into differentiation. But the problem is that there is two time inputs, not just one. So how can we find the position at a given time if we have two time inputs? Well, think about the action of squeegeeing, and think about the start and the finish. Because, like, as you are squeegeeing, the finish line keeps moving, but the start time stays the same throughout the squeegeeing. Which means that our T1, our starting time, is kind of irrelevant because it's a constant. So instead of writing T1, I'm just going to write S for, like, some variable start. So if this is the start time, right, and I'm right here at the start, then instead of drawing, like, the t-axis right here where the position is 0 right here, it would make sense where I draw it right there, right? Because if this is where I start, then right there where I am should be where the baseline starting position is. So if we give some number to our T1, or some time that we input, then the area between the start time and the time that we give it is just the distance between the start time and the input time. Which, if you think about it, is exactly what this graph is telling you. It's the distance between the start time and some other time. Because we said that this is the new baseline, that this is the 0 position. So, just to recap. So, given some arbitrary start time, if we have some time after or before this start time, the way to find the position at this T1, where on this position graph, where this point is at position 0, then you just find the area between the start time and T1. Then finally, if we want to calculate the entire position graph, and I know when you integrate that there are infinite position graphs, but this is a specific position graph where this S at time S, position is 0. So that's the position graph that we are graphing. Even though it is infinite, this start time basically says which position graph we are graphing. Then what we could do is find the area from the start time to all the other different times that we want to graph. Alright, so now we know what to do when we differentiate and integrate. Differentiation is just looking at the slope at each point, and integration is looking at the area from each point to whatever starting point you have. But now the question is, how do we actually compute it? How do we compute area under the graph? How do we compute slope at a single point? Doesn't slope need 2 points? Now what we could actually do is, instead of trying to find the exact slope in the exact area, we could actually find the approximations for them instead. So let's start with differentiation first, okay? So let's just say you have some point, let's just say right here, you want to find the slope at that point. And another way to put it, what's the slope at the line that just touches the curve at that one point? Now what we could do, instead of finding the slope of that point directly, we could just put another point on the graph, then find the slope of the line that connects those 2 points, right? Now the slope of this line isn't really a good approximation for the actual slope, so if we wanted a more accurate slope, then what we could do is move that dot more closer to the original dot. Now you see here, once I brought my point to my desired point, then the slope of the line has become a better approximation for our desired line. And just some terminology, this line that's connected by 2 points on the graph is called a secant line, versus the line that just touches at that one point, which is called a tangent line. So that's how you approximate differentiation. So now how do you approximate integration? How do you approximate area under the curve? I know I didn't learn any formula for the area under the curve, but I know I learned the formula for something as simple as like rectangles. So maybe what we could do is fill this area under the curve with something we know like rectangles, and just fill it with a bunch of tiny rectangles to approximate the area. Let me show you what I mean. So let's say that we want to find the area from like right here to, let's just draw a boundary right here, from this time to this time. So what's the area in this time interval? Like I said, we could just start filling it up with tiny rectangles. So maybe I might add the first rectangle here, then I might add a rectangle here, then maybe a rectangle here, then a rectangle here. And again, it's not a perfect approximation, but as you keep adding more and more rectangles, and as the width of each rectangle goes lower and lower and lower, we get better and better approximations. Okay, so now, if we have a position over time graph, and we want to have a velocity over time graph, this is what we would do to generate that velocity over time graph. And if we had a velocity over time graph, and we wanted a position over time graph, this is what we would do to generate that position over time graph, or at least the shape of the position over time graph. But what if instead of having just some regular function, you have a formulaic function? Which, what I mean by that is if you have some input and you plug it into some formula, the output of the function is just the value of the formula when you plug in the input. Like for example, if the input is just the value of some variable x, then the output is going to be the value of some formula with the input of x. Whereas right here, where you're looking at the velocities for all the different times, right here, you're looking at the x squareds for all the different inputs of x. Now I'm just going to generalize for the output formula as just f of x. Okay, so we have this function, which is defined by this formula f of x. And I'm just going to draw some graph that could be described as f of x. Now if we go back to differentiation and integration, we are no longer trying to compute some graph, which is the derivative of this graph. What we are trying to do is come up with some formula which is the derivative of our main formula f of x. And the way we normally denote the derivative of f of x is we normally just say f prime of x, or f with the apostrophe x. And normally, if you were to integrate f of x, meaning go the thing below, you would normally write capital X, which if you differentiate capital f of x, then you just get regular f of x. But before we get into coming up with new formulas from old formulas, I really want to nail down the idea of rate of change, because I've just kind of thrown that out there as kind of like the main idea of this, but like, what is the mathematical meaning of a rate of change? Well, what is rate of change? What is speed? Well, when I think of speed, I think of meters per second, miles per hour, right? Like, if I have an hour, how many miles does my position change? If I have 1 minute, or if I have 1 second, how many meters does my position change? So the way I like to think about it is like, given some change in time, what's the change in position? And if I'm talking about any function, rate of change would just be, given some change in the input, what is the related change in output? And if we're specifically talking about formulaic functions, then rate of change is just, given some change in x, what is the related change in f of x? And it's kind of accepted that whenever you talk about a change in some variable or changing some output to a formulaic function, that you denote it as delta x, delta f of x, which is, it's written as triangle x, triangle f of x. Well, then where does the rate of change or slope come in? Well, if you have some change in x and you have a really high slope, which means the rate of change is high, you have a really high slope, then the change in f of x is going to be a lot greater than the change in x. But if the opposite is true, if you have a really shallow slope, then the change in f of x is going to be a lot smaller than the original change in x. So we have some change of x. Then with that change in x, we are able to get change in f of x. The way we get from change in x to change in f of x is we multiply by slope. We multiply by the rate of change. Now this is the mathematical idea of rate of change. Now I know I've been describing this for the differentiated process, so let me describe it for the integration process. So again, going back to the squeegee, if we've already collected this amount of area, and we want to collect a little bit more area, and that little bit more is just delta x, because it's the change in x, right? And by doing this little bit more x, you may be able to get a little bit more area out, which I'm just going to call delta area. So you have some change in x that determines the change in area. And how do you get from the change in x to the change in area? Well, you multiply by the rate of change. You multiply by the slope. You multiply by the velocity. You multiply by the height of this rectangle, which the height of this rectangle is just f prime of x. Oh yeah, and because we're dealing with integration, because this is our function that we're starting with that we know, we just call this just regular f of x, and the integral of just regular f of x, like I said, is capital F of x. So if we go back to rate of change, so we're multiplying the change in x by f of x, and we get the change in area. Now, if we think about it, multiplying the base times height, we get the area. Does that check out? Yes, it does. That's just the area of a rectangle. So everything checks out there. That's good. Now, hold on. Let me pause for a second, because there's like a big plot hole in my scheme of integrating and differentiating. Because remember, we are working with formulas, and we're trying to come up with another formula from our original formula. Then why are we using approximations? Why are we using concrete changes in x and in f of x? Because I don't want to go for an approximation of a formula. I want to go for the exact formula. But we are never going to get 100% accurate formulas with concrete changes in x and concrete changes in f of x. So what do we do? Now, what I would do is, instead of using concrete changes in x, what I would do is just have the change in x get infinitely small. Have these 2 points get infinitely close to each other. Now I know what you might be thinking. This is really weird. This is very strange. This doesn't make sense. How can 2 points be infinitely close to each other? This just doesn't make sense. I'm scared. But the thing is that the train from making sense has already left the station. Now we're dealing with cold, hard formulas. Now, thinking about concrete changes does have its place in time, but this is just not one of those times. So, if we're talking about infinitely small changes, instead of using delta x, which means finite change in x, we're going to use delta's little sister, dx. So now that we know what rate of change is mathematically, now I want to get into how to notate differentiation and integration. So like always, we're first going to start with differentiation. Now I know we already have f prime of x, but I want to see a way to write this mathematically using our rate of change formula. So as we know, the derivative of this function is its slope, is its rate of change. So if we can isolate this slope, then we have slope is equal to something with df of x and something with dx. Then we can have a formula that's defined as slope, which could be defined as f prime of x. So if we divide both sides by dx, then we get m is equal to df of x over dx, an infinitely small change in f of x divided by an infinitely small change in x, which is where we get rise over run. Okay, so if we have some formula, f of x, and we wanted to find the derivative of the formula, then we could just plug it into this equation, and then that should give us the derivative of the formula f of x. It should give us f prime of x. And just to make it really easy to plug any formula into this equation, I'm just going to drop this f of x down and just have d over dx of f of x, where I just take the f of x and I put it in front of the d over dx. And just remember that this d is still connected to the f of x. This is just shorthand, so that if I have some function f of x, I could just plop in front of it d over dx, and that's the same thing as put in parentheses above it. So this is just shorthand, but just remember what it means. This is how you differentiate f of x. Easy peasy, right? Well, unsurprisingly, it's just the calm before the storm. So how do you notate integration? Or more specifically, how do you notate the different kinds of integration? Because remember, there are actually 3 different types of integration. Because the first one is just the base operation. It's just the distance traveled on a position graph between 2 time periods. And this second way actually does generate a position graph, but this way also needs some start time put into it. And the reason why you need to put in the start time is because remember, when you're integrating, technically there are infinite position graphs. And that brings me on to my third and final way, which that instead of just generating one position over time function, you're generating all possible position functions, which you can do like in 2 parts. First, you generate the shape of the graph, and then the second one, you take that shape and you duplicate it everywhere that it can possibly be. Okay, so let's start with the first one. How would we be able to notate just the distance traveled between 2 time periods, or the area between 2 time periods, or the area between 2 x values? So let's say I have 2 values, x1 and x2, and I want to find the area between those 2 values and the area between the x-axis and the area under the curve. And remember when I talked about the mathematical meaning behind rectangles, that it was the base times height is the area, the f of x times dx, the infinitely small change in x, because now that we're dealing with formulaic functions, these need to be infinitely small rectangles. So it's dx times f of x, which is equal to the area, infinitely small change in area. And that's for basically what I have. D area is equal to f of x times dx. Now remember, what we're trying to do is once we have all these infinitely small rectangles, we need to add the area up, right? Because remember, we have a lot of small changes in area, so what we need to do is add those changes in area up. So in total, the way we get area is we need to sum up all the different fx times dx. Now how do we write that we're summing it up? Well, actually, because mathematicians are pretty lazy, what we do is just put an S at the front to show that we are summing up everything here. And once we do that, this will no longer be dA, it would just be A, because we are summing everything up. But remember, we're not just summing up all the different rectangles in the entire world. We're only summing up the rectangles from x1 to x2. So with this new S notation, the way we write from one input to the, from one bound to the next bound, we just write on the bottom and front, x1, and at the top, x2. So what this is saying is if we want to find the area under curve from x1 to x2 of some formulaic function, then the way we would write how we would want to figure it out is this S notation from x1 to x2 of fx times dx. And if we think about the next way that we write integrals, where we have one start area and we let the finish area, I guess, go throughout and graph it all the way around. So in this example, again, we are adding up the area of the rectangle with sides f of x and dx, but what are the bounds of this second way to integrate? Well, remember that we always started at some constant s, because we're going to let that first number be constant and let the other one be the input of our function. So at the bottom of our sum, I'm just going to put the constant s. So then what do we put on the upper bound? Well, do we put x because that's kind of where this is going? Well, if you think about it, we already kind of have an f of x, and it kind of really needs to be separated so that it doesn't get mixed up between the upper bound and the function of x. So instead, I'm going to use a new variable, let's just say u, as the upper bound. So I can make u anywhere, and I can choose some starting point, and what this will tell me is the area of the f of x graph from u to s, or from s to u. And finally, what is this integral equal to? Well, what does the integral do? Well, I guess it gives us the position graph with some specific start time. And in this case, because we're going down, it would be capital F of x. But instead of the input being x, remember, we changed the input to be, instead of x, where it's being u. So it would be f, where the function capital F of u is equal to the integral, the sum of rectangles from the lower bound being the start time and the upper bound being the input variable u of the rectangles which have a height of f of x and a width of dx. And then a final type of integral, remember, is sort of like our holy grail of integral types. Whereas the integral type before just gave us a concrete function, this function gives us every single possible function. And remember, there are infinite possible integrals you can get. So this third type gives you all of them. And the way it starts off is the same way we've been doing for the other two. We just say the sum of the rectangles of the height of f of x and then the width of dx. But right here, the idea of summing up rectangles with a height and width kind of loses meaning, because in this third type of integral, we aren't really using the analogy of adding up rectangles. We're just talking plain old integrals, because we're just doing a fellow swoop of all the different integrals. But you might think that, well, does this second type of integral do that? If you set the starting time to every single possible number, doesn't that give all the different possible types of integral graphs? And the answer is actually no. And here's why. Because let's just say that there's some position graph where like I'm the starting point and the object just moves around above the starting point. That is a plausible position over time graph. And there is a velocity graph that mirrors that position over time graph. But the thing is that this function will never compute that position over time graph given its correlated velocity over time graph. Because what this is always doing is looking for a start time, and that position over time graph has no start time because it's never at the starting point. So that's why we need this third integral type, to just get all of the different integrals at once. And that's why we're writing this the way it is. We're not really saying that this is exactly what the math is doing, we're just saying that it kind of has the essence of integrals in it. And then what do we put on the bounds on the top and bottom of the integral, like we have done with the other two? Well, for this we don't actually put any bounds, because again, we're not actually using this as the sum of rectangles. It just kind of looks integral-ish. This sounds weird, but it's like because it kind of looks integral-ish, it kind of has the essence of integrals, we just kind of use it for the all integral whatever. So then how do we find this all-encompassing integral? And like I said, this integral has two parts. The first part being the shape and the second part being the all-encompassing absolute location. And for the shape I have just capital F of x, and using this function above, and specifically using this where the s is equal to 0. So it's basically the capital F of x function, the integral function, where when the time is 0, the position is 0. So that's just this function. And then the second part, I just have plus c. And the c just stands for a constant. But this is not just a constant. This is every constant. Where this c constant tells you where you are at like time 0. And that's why we had on capital F of x, time 0 is position 0. So that when we add plus c, that when time is 0, c tells you where you are. And that's opposed to what s is saying, where while s is telling you when position is 0, c is telling you where time is 0. And using these two parts, capital F of x, which just gives you the shape, and the plus c, which just takes the shape and then puts it everywhere it can. Okay, so now that we have a really good foundation for formulating functions and how they work in the world of integrals and derivatives, now we can actually get to what we were trying to do in the first place. Come up with a formula that is either the derivative or the integral of some original formula. So let's start with derivatives. So how would we be able to come up with a way to generate one function from the original function? So remember, the way we got the derivative of the formula f of x is we have some infinitely small change to x, then that infinitely small change in x causes there to be an infinitely small change in f of x. And what you do is you divide d of f of x by just d of x. And notice that the d of x, I know what it is. It's infinitely small. I have control over how small it is. But d of f of x, that's kind of depends on what d of x is and also like what f of x is. So maybe it might be better if we expand out d of f of x, because remember, d of f of x is still a change in f of x. There are two values that you're subtracting, the bigger one from the smaller one, or I guess the smaller one from the bigger one too. But so I guess let me write that out. That feels fake. When saying that out loud, that feels fake. So can you guys like let me know how I could have reworded that better? Because I'm not really 100% confident on this step, so this is just the one thing that just let me know how you guys would say this. Anyway, let me get back. So before we get into what d of f of x is, let's first start on what d of x is, the expanded form of d of x. So if we think back to the graph, if we have some like change in x, which I know this is finite, and dx is supposed to be infinite small or 0, but this is just enlarged to show what I mean. So if the change in here is dx, then if the first value is x, then this value would just be x plus dx. And then the change in x, and I know the change in x is dx, but if I just write it out, that this minus this would just expanded would be x plus dx minus x. Which I know the x can cancel out and you just get dx, but let me just keep this like this, okay? Then where it gets interesting is if you think about what these values turn out to be on f of x. Because remember, the way we get d of f of x is we just plug in these different values that we get to make d of x. So now that we have these two values that make dx, we can then get the two values that get d of f of x. So if this is x, then this would just be f of x, right? And if this is x plus dx, then this would be f of x plus dx. And then finally, if we wanted to find the difference between them, then we wanted to find the change in f of x, then we would get the top number minus the bottom number, or f of x plus dx minus just f of x. So the first part we have just the change in x, which we already knew was dx because that's what we're inputting change as. Then here we have the change in f of x, or d of f of x, which right here we could see that the change in f of x is determined by d of x. So that means I could just take this and just replace it for the d of f of x, where now, instead of having two infinitely small values, I only have one infinitely small value. And this is exactly what we want. Now, if we have some function, then we could just plug it in where we have f of x and f of x plus dx, then we can just come up with the formula. Let me show you how. So let's say our formula was just x squared. So you see here that I basically just replaced all the f of x just by x squared. And remember that the d of x is infinitely small. So because we're just working with expression, can we just plug in 0 for d of x? Well, if we did, for the numerator, we would get x plus 0, or just x squared minus x squared, which is 0 for the numerator. In the bottom, we just get 0. So we get 0 divided by 0, which we can't do. But if we do some rearranging around, this expression can actually turn out to something where if we plug in 0 for d of x, then we can actually get something other than 0 divided by 0. Let me show you. So first what I want to do is this x plus dx squared is to expand that out for x squared plus 2x dx plus dx squared and then minus x squared. So first thing I notice is that the x squared here and the minus x squared here cancel out. They subtract to 0. Then everything else here has a dx in it. So I could just divide dx here and then take that to turn it into a 1. Then I just have 2x plus dx. And now if I try to plug in 0 for d of x, now I just get 2x. No worries. So because d of x is 0, then I just have the formula of 2x, which this is equal to the derivative of x squared. So we turned this formulaic function, this formula of x squared, we plugged it into this formula. And then when we worked some things out, we were able to get something that when you plug 0 into dx, it wouldn't just get 0 divided by 0. We could just forget about the dx and then get a function on its own, which is the derivative function to x squared. So we went from x squared, we took the derivative, and then we got 2x. Which right now, I don't really fully understand why it works. I will later probably figure out an idea of a way of thinking about why this works. Because the 3 Blue 1 Brown competition deadline is coming up, I'm just going to leave it at that. But anyway, enough further chit-chatting, let's just push forward. So integrals, how do we find some definition for an integral? The thing is, there is no definition for the integral, it just doesn't exist. There's no clean, easy, simple way of finding the capital F of x plus c if you have some base function just f of x. There's like no easy way, there's no just definition to get you that f of x plus c. Technically just f of x, because if you just have the formula f of x, you always just add plus c when you're integrating like this. So there's no way of getting just this capital F of x. Now why is this? Well, actually I have no idea. I've tried looking into it. I couldn't find an answer for why this isn't the case, why there's no definition for the integral. Like, if you know, please let me know. Please, like, comment or whatever, because I would really like to know why this is true. But there are ways to get around this. Like, there are some, like, tricks where, like, if your function looks a certain way, you can manipulate it to get the capital F of x. But there are only, like, a limited number of them, and they don't apply to everything. So there are some formulas which can't be integrated to get another formula. And also these tricks are kind of repetitive, and I'm not going to go through all of these tricks of how to do integration. So this is the last time that we're going to see integration, but just know that there is a path where you can look at these tricks and there are ways around that there's no definition. However, we're not done just yet, because there's still some things that I want to look at in the derivative definition. Now yes, technically you can if you just have any formula, no matter how big it is, you can just plug it into there and you will be able to count out the derivative of that formula. But like, for example, if you have two formulas that you already know the derivative of, but you're trying to find the derivative of the sum of the two formulas. Then to get the derivative of the sum of the two formulas, what you can actually do is because you know the derivative of both of them, take the derivative of each one separately, then add them. And that itself is called the addition rule for the derivative definition. Now that doesn't work for everything. For example, if you're multiplying two formulas, you can't just take the derivative of both formulas separately, then multiply them, but there is kind of like a formula that you can use to like shorten the process, and that is called the product rule. Now I'm not going to get into all of these rules and why they work and all of that stuff, but there is one that I really want to focus on, and that being the chain rule. So let's say you have two functions, f of x and g of x. And now you know the derivative of f of x by itself and g of x by itself, but you want to figure out what f of g of x is. So you want to take the derivative of this. So how would you do this? Well, if you remember back to what I defined as a rate of change, remember I said that there's a small change in the input, a corresponding change in the output and the relation between those two. So we start with some change in x, and I'm just going to put dx because we're working with formulas and we're working with infinitely small changes, but just remember that this still is a change in x, so I'm just going to refer to it as a change in x even though it is technically an infinitely small change in x. So anyway, so now that we have this change in x, we can now get out a change in the output, which the output is f of g of x. And remember what the slope is what you have to multiply to this change in x to get the change in f of g of x. But if you think about it, what this is, from going from a change in x to a change in f of g of x, can actually be broken down into two parts, right? Because we go from a change in x to a change in f of g of x, well, we could start by going from a change in x to a change in g of x, then from a change in g of x to a change in f of g of x, right? So we could start with a change in x, but instead of going directly to a change in f of g of x, we could stop halfway by just saying, looking at the change in just g of x. And the way we get from d of x to d of g of x is just the slope of g of x, just the derivative. So g prime of x. Now that we have dg of x, we can actually start there and then get to gf of g of x. So now that we have dg of x, we could just pick up from there. So we know what dg of x is, and we want to go from dg of x to df of g. And the way we get from dg to df of g is we multiply by the slope, we multiply by the derivative of the function f. And that would be the derivative of f with the contents of g of x. And this is because our input is g and our output is f of g. So the derivative is just f prime of g. So just to recap, so we started at d of x, then we multiplied by g prime of x to get to dg of x, then from here we multiplied again by f prime of g of x to get to our result, df of g of x. So first we multiplied by g prime of x, then we multiplied by f prime of g of x. So finally, if we want to get from d of x to df of g of x, then what we multiply is g prime of x, and then we multiply by that, then we also multiply by this, f prime of g of x. So if we wanted to differentiate the function with the input of x and the output of f of g of x, then the derivative of that function is g prime of x times f prime of g of x. Or another way to think about it, the derivative of the inner function times the derivative of the outer function keeping the inner function. So this is what we call the chain rule, because we're chaining up functions. And this is why. Now, this is the last thing that we're going to touch in this video, but I kind of find it a little funny that the first day when I was actually learning about derivatives, I kind of learned a little bit of the idea of what derivatives are, but then immediately after that, I learned basically how to do derivatives, like the power rule, for example, like how I showed that x squared, the derivative of x squared is 2x. And I learned the rules of differentiation, like the chain rule, and the product rule, and the addition rule. But I remember when learning about the chain rule, thinking to myself that I didn't really understand why it was true, because they just said, hey, if you see this is the formula that will help you differentiate this formula, this stacked formula, this chain formula. So it's good if you memorize this formula so that whenever you encounter this, you could just pull out that. but they didn't really explain why this formula is. But even though I've demonstrated that there is understanding, there is reason behind this formula, they just kind of glossed over it and went on to the next rule. And I felt like that this was kind of like a pattern that I was noticing. Like obviously I couldn't figure out what area had to do with integration, and also I was really confused about why there was 3 different ways of doing integration, because with differentiation it was really easy, you pushed a button on a formula and then you got the derivative. But with integration, why were there 3 different ways? And I believe why this is because in school, what the teachers really want you to do is to pass the test. They want you to solve the equations. They have an entire course to teach in just a semester. So after I learned calculus, it kind of set some time to myself to just think about why all these facts and formulas were true in my head. And the definition, I'm still in the process of thinking about why these things are true. So I guess you could say that I heavily learned how to do calculus, but I wasn't really taught too much the concepts of calculus, which I would argue is what calculus is, which means I had to find the concepts of calculus, which I guess you could say means that I was able to teach you calculus. Hey, you know what? I actually think I'm kind of getting a little hot, so I'm actually going to take this off. But anyway, see ya.